All right, so there's still some things that I kind of wanted to go. So, for example, quickly, the rearranging. What is the rearranging equation part first? I'll just do the rearranging part. So, let's say, all right, so if I gave you, how would you write, let's say for this example here, right? How would you give an expression to represent finding the concentration of, let's say, propanol? If I said to you, write an expression to find out the concentration of propanol, and they've given you the Kc, right? But they just want you to write an expression. How would you write that? So we just do that right now. All right, I've seen that you paused the video and you've done that. So let's say propanol, right? So if you've already done this, sometimes they might even give you something to do this. But if you've already done this, and you already know it's this, first of all, I'd write out this first of all if I was doing this. That's me personally. I write out the Kc first, and how do I go from here to here? And it's like, oh, I just need to, I need to get this, rearrange the equation, and just substitute that for that, and that's it. It will just be propanol. If I was to rearrange that equation, is equal to the numerator remains the same. It's literally just rearranging your equation. Oh, do not disturb. Right. Sorry about that. That probably was my KFC menu actually. I've had a KFC in a while. Anyway, H2O4, H2O. That the numerator as before stays the same. But this part here, O to the power of 5. Actually, you know what? Even just to show you here exactly, you can just really make a difference. But Kc is now here. O2 times 2, O2 to the power of 5. But if you ever got like, I mean, rearranging an equation is going to be very, very simple for you. But I'll give one last example. And then I'll go on to the next part, which I want to explain for. So let's say if I wanted to go for, let's say if I wanted to if I want to work out the right expression for this, for the, to find a concentration of CO2, right? Same thing. I would first of all write that first, because that's the easiest part to go through first, and then rearranging that equation, I would find that CO2 cubed. I mean, I can do it in one go, but just for people that can't see it directly, I'll just go CO2 cubed. I can just see it's a cube. It's just a cube root of cube root of Kc times by CH propanol times by O to the power of 5 all over H2O to the power of 4. Some people can't see that directly, so I'll just show you what it is. I'm bringing the denominator over to this side, so I have to multiply this. So it'll be Kc multiplied by, give a bit of space here because there is a bit of multiplying there. There's something I'm going to do. I'm going to do a root there, so I have to leave a bit of space here. CH2, CH2OH, and then O2 to the power of 5. Alright, that's just me bringing this over, multiplying the denominator there to bring over to that side. And now I'm left with CO2 cubed over H2O to the power of 4. But I just need the CO2 part, right? So this over H2O to the power of 4. Right, but this is a cube. This is CO2 cubed. If I just want the CO2, I need to cube root this. And then that's your expression for this. It's just basic rearranging of maths. Right, so now the last part I'm going to go over is something called, it's a part of your exam where you need to understand how to find out the value of Kc. And now they give you, what they do is they give you, in your reaction, right, you have to think about this. You have your moles that you have from your reaction, but you also need to work out something called the equilibrium moles, which is the moles that you have of your reaction whilst it's in equilibrium. And that's different, right? And it's very easy to do. We have something called an ice table, right? An ice table is an ice table is just a way of working out your amount of moles in equilibrium. So let's say we have this same reaction, right? This same reaction, they tell us that we have, let's say 0.1 moles of this propanol, right? 0.1 moles of propanol, and we have, let's just say 0.5 moles of O2, just 0.5 moles of O2. We have, and then they will tell us how do you, and this is not the equilibrium moles. This is just the amount of moles that we have, and then the amount they'll tell us one equilibrium mole, right? They'll tell us one value in equilibrium moles, and that would be, let's say we have our equilibrium moles of CO2 would be, let's just say 0.3, right? We have 0.3 moles in equilibrium of CO2. So how would you go about this, right? So first of all, what you need to understand from this reaction is that, so we write out our initial moles. The I represents initial, C represents the change, and then the E represents the equilibrium mole. So our initial moles is going to be 0.1, 0.5. Our initial moles of our products is going to be 0 because initially we have 0 moles of our products. Then we're given one equilibrium moles, and that's 0.3, right? So then if I wanted to work, what's the difference between 0 to 0.3, right? In this case, to work out the change, this change allows us to work out the equilibrium moles. Ideally, you want to get the equilibrium moles for all of them, but how would you get that? And that's what you do here is simple as like, what's the difference between 0 to 0.3 plus 0.3? But be wary, there's different amounts in moles from 0. This is 3 CO2, and that's 4 CO2, right? So this is that's times by, that's 3x, right? So if if that's 4 CO2, how are we gonna go? So we have to go 4 over 3. We have to times this by 4 over 3 because that's 3 moles and that's 4 moles as given our equation, right? 4 over 3 times by 0.3. So 4 over 3 times by 0.3, which is just gonna be 0.4. And we already know this because that's 0.1 there, and that's 3 moles. It's very easy to do that. So that's 0.4 moles. So that's plus 0.4. Now don't get confused now. I'd actually like people to do this when they separate them out. In our products, we're always going to form products. So our change would be a positive increase. However, when if it's a reversible reaction, this can change. But in this case, we're forming products. If we're forming reactants, we just reverse it. But in this case, we're trying to form products, right? So if that's the case, our change would be a positive increase. But if we're increasing our products, which means that we're decreasing our reactant. And in that sense, if this is if that's the case, then we would just be minus 0.3. But of course, this is let's say this is 1 mole. We've only got 1 mole of CH3, CH2, CH2OH. We would take away a mole, so it will be 0.3 over 3 because there's 3 moles, right? We need to get from there's a 1 to 3 molar ratio, right? 1 to 3 molar ratio, and we know we have 0.3 here. We're trying to work out what this is here, so it'll be 0.3 minus 0.1. So 0.3 over 3, which is 0.1, so it's minus 0.1 in this case, or it's just minus 0.1, and that's 0.1 minus 0.1, that's just 0 in this case. And in this, if you times that by 5, because it's a 1 to 5 molar ratio, that's minus 0.5. And this is an example. I'm just giving an example, but this is just an example for you to kind of understand it. I probably would use a different example of it because I might have confused some people when doing this. But this is pretty much what it is. I should have got the equation a bit lower down so it makes it, instead of scrolling up and down. But in this case, we have 0.3 moles in our equilibrium moles. We have 0 moles of propanol and 0 moles of O2. I have 0.3 moles of our CO2 and 0.4 moles of water. and that's the amount of moles we have in equilibrium. Should I use a different example? I think people get generally what I'm trying to do here. You just if it's for the equilibrium moles, right? We're increasing it by but we're just trying to show the change. They tell us that we have 0.3 moles of our product in equilibrium. So to go from zero to 0.3, that's plus 0.3, and then we carry that same method. We know the change, so we have to take into account it's a 3 to 4 molar ratio from here to here. Therefore, we'd have to times it by 4/3. That's plus 0.4, and we use up plus 0.4 so to get 0.4 here. And then when we have our reactants, it's the same principle. It's just that it's a 1 to 3 molar ratio from here to here. So we have to divide this 0.3 by 3 to get 1 because it's a 1 to 3 molar ratio. And the fact that when we're increasing our products, we're decreasing our reactant, and therefore our change will be a negative, will be a decrease. So it'll be minus 0.1. And then in this case, it's a 1 to 5 molar ratio, so it's minus, times that by 5 to get minus to get minus 0.5, and when we decrease that, be 0. Now in other cases, in most examples that you get in your exam, it won't be 0, 0, 0.3, 0.4. You can get a value, but all you're doing is just taking away that value by a change to get equilibrium moles. Now, if this confuses you even more, watch allochemistry videos, because I'm probably not going to go over this again unless I get an example. But I haven't got an example with me today. I'll probably go for a video where I can finally get a good example to show you what I mean. But I've got some exam questions here that hopefully might help you out. So I'll just go through those. Alright, so this is a how many marks is this now? This is 7, 8, 17 minutes, right? So 17-minute paper. I'm going to try and go through this. So I'm not going to include this part here. Don't worry about that. From question 4 to to the end, I'll let you guys give a head. So just take a pause of this. That's the first part here. That's the next part here, in case you can't see the rest of it. That's the next part here. This is from physics and maths tutor, so that's just where I got them from. And then this is the last part here. So pause the video now and try and answer those questions. This is just to help you out, so obviously don't feel like you have to do this, but if this helps you out, then of course go ahead and try it. And yeah, so I'm going to set a timer of 17 minutes. Let's go. So I assume you've done the questions, and I'm going to start trying doing it now. So 1 mole of diester with molecular formula C7H12O4 is added to 1 mole of water in the presence of a small amount of catalyst. The mixture is left to reach equilibrium at a constant temperature. So that's our equation here. At equilibrium, X moles of ethanoic acid are present in the mixture. Complete table 1 by deducing the amount in terms of X of the diester, water, and diol present in the equilibrium mixture. So pretty much they're telling us this is just an ice table, but just they've taken out the C part, but ideally the C part isn't actually necessary. It's just to help you out, right? They're telling us they have X moles of in our equilibrium mixture of our acid, right? Therefore, we don't have a value, but we know it's X, right? So it's represented by X. It's a 2 to 1 mole ratio from here to here. So it'll be from 0 plus X, but here is half of that. So it'll be the difference would be here. The difference is plus X. This would be the difference. This would be half X, or plus X over 2. 0 plus X over 2 is just X over 2. Now we're going to our reactant side. Same thing, but we're taking away. We know this is going to be minus X, because it's a 2 to 2 or 1 to 1 mole ratio in that sense, or 2 to 2 mole ratio, same thing. So this we have 1 be minus X, so it'll be 1 minus X. and in this case it's half, is a 1 to 2 model ratio, so it'll be half of this, so it'll be half minus half x, minus x over 2, right? That's what that would be our C, and therefore it'll be 1 minus x over 2. I'll scribble this part out because, you know, make it clear, because that's not what they're looking for there. But that's all it is. Then I'll deduce the structure of the diester in part A. Deduce the structure of the diester in part A. See, in physical chemistry, how should I say? In physical chemistry, people get complain, say, why is there organic chemistry and physical chemistry? Your paper is part physical chemistry and part organic, so they'll be mixed into time. But either way, these are very simple ones you need to do. So what's our, let's use our structure of a diester in part A. So our diester is that. Okay. So first of all, I'm going to need to have one, two, three, and then this 1, 2, 6, and then 7. So this needs to be H2, CH2, CH2, yes, 3, 4, 5, 6, 7, yes, yes, an isodiester, yes. All right, so next question now, a new equilibrium mixture of the substances from part A. Can you guys see that? Yeah, a new equilibrium mixture of substances from part A is prepared at a different temperature. So it's the same reaction, but it's just a different temperature now. Table 2 shows the amount of each substance in this new equilibrium mixture. The value of the equilibrium constant is Kc is equal to 0.161 at this temperature. Calculate the amount of water in moles in this new equilibrium mixture and show your working. Right, so they just do they've given you the value for Kc, and they want you to rearrange to get your to find out your equilibrium mixture for water. Do we make out? No, we didn't do that. So the first thing I would do in these types of questions, it was do, so write Kc equal to, it would be, some people can see it straight away, but for people that are just doing this for the first time, do it like this, helps you out. Write out what the actual expression is first, and then, so, HO, that, CH2, that's a bit scruffy, you know, sorry about that. That's meant to be a bracket. CH2 3OH all over C7H12O4 and then H2O squared. Right. Now we want to, they've given you the value case, now you need to work out just for H2O. Some people can see this directly, but if I was to rearrange that, H2O will just be the square root. It's just, you're just swapping this for this, and it's going to be a square root because you have to get rid of that square. So it'll be the square root of CH3, CH3 COOH squared HO CH2 3OH over C7H12O4 times by Kc. That's it, and then they've given you now you have your expression. Now you just substitute your values in that they've given you, and then you would work out your value. So lucky for you in this situation, there's an equal number of moles on either side of the reactants and the products. So you don't actually have to work out the concentration. You can, because the moles in this case, you can treat the moles like the concentration because there's an equal number of moles on either side of the equation. So how would I do this? I would say what's the CH3? So diester 0.971 squared, because we're just substituting our values in now. The no, my bad, sorry. My bad, sorry. Yes, sir. 0.452, making sure they didn't make any mistakes earlier on, times by 0.273. So 0.452 squared times by 0.27. Write it down here, mate. It's too messy. It's too messy. 0.452 squared multiplied by 0.273 all over 0.971 times by the value of Kc, which is 0.161. H2O. And our value for in moles will just be, just put that in, jot that into your calculator. So 0.452 squared multiplied by 0.273 all over our products. Zero 0.971, 0.161, 0.5, and that's 0.597. It's the three significant figures because they've given us three significant figures in our question here. So 0.597. Which statement is not always correct for a reaction at equilibrium? The concentration of reactants and products are equal. The equilibrium can be achieved starting from the reaction. That's just no. The rate of the force reaction is equal to the rate of the. These are in dynamic equilibrium, so this is the only one that makes sense. Remember, it's not always correct for a reaction. The concentration of reactants and products are equal. Only the concentration of reactants and products are equal. Not always the case. No, not always the case. Hydrogen gas can be made by reacting ethanol with steam in the presence of a catalyst. Give an expression for the Kc of this equilibrium. So Kc, just, as I said before, products over your reactants, it would just be carbon monoxide squared times by H2 to the power of 4 all over our reactants, which is C2H5OH times by H2O, and that's it. And our units for Kc, remember, you're getting moles to the power of 6 over moles squared, so that's going to be overall, it's going to be time moles per dm cubed to the power of 4, which is the same as moles to the power of 4 dm to the power of minus 12. For people that don't see that. And now you can see that 4 minus 3 times by 4 minus 12. I believe this is the last stretch. So a table shows the amount of each substance in an equilibrium mixture in a container of volume, which is volume 750 centimeters cubed. Calculate the Kc. They've already given us they want us to work out what now? They want us to work out the Kc. We already know the expression. Now we just substitute. We have to actually work out the concentrations first. So concentration of ethanol C2H5OH. 0.075 over 0.75. Remember, that's in centimeters cubed, so it's 0.75 decimeters cubed, which is just 0.1. 0.1. I'll make it here. Of concentration for H2O. Remember, our moles on either, in this case, there's a 2 to 6 difference between our reactants and our products, as every, so it's not equal on either side. So we have to work out the concentration. So remember, concentration is equal to moles over the volume. Our moles is equal to 0.156 over 0.75. 0.208 for carbon monoxide, 0.11 over 0.75, 0.11 over 0.75, 0.147. This should be 0, 0 because it's three significant figures I'm seeing. They're giving you that, so that's equal to 0.147, and then H2 gas, or it's 0.22, just double that, so you can just kind of just assume double, but 0.22, we'll just double that, so that's 0.293. Now we've got to substitute that into our equation. We don't have to write the Kc again because you've already said that in the previous question. That's just equal to products over reaction, so carbon monoxide to the power, carbon monoxide squared, so 0.147 squared multiplied by H2 gas to the power of 4, 0.293 to the power of 4, all over our reactants, 0.100 times by 0.208, 0.208 Kc is equal to, make sure to have enough time to answer the rest of our questions. So 0.147 squared multiplied by 0. Just put answer to power 4 over 0.1 multiplied 0.208, and we should get that is that? Wait, 0.293. Yeah, sorry, I made a mistake for some reason. 7.66 times 10 to the power minus 3. And I'd say just moles. Make sure to put them. I just put the units here just in case. Moles to the power 4 dm to the power of minus 12, just in case they don't give it to you. So 7.66 times 10 to the power of minus 3 moles to the power of 4 dm to the power of minus 12. Right, if in case you find yourself where you don't have a lot of time, I still speed through this. I was just talking too much for this. So the pressure of the equilibrium mixture was increased by reducing the volume of the container at constant temperature. Predict the effect of increasing the pressure on the equilibrium yield of hydrogen and explain your answer. Predict the effect of increasing the pressure on the value of Kc. Increasing pressure on the value of Kc, I can just easily straight away, no effect. So pressure has no effect of on Kc. It doesn't affect Kc. The effect on equilibrium yield. So if I'm increasing the pressure, there's more moles of our products than our reactants. So it would decrease. Our yield of hydrogen would decrease because there's more moles of products than reactants. So increasing the pressure causes equilibrium to shift to the left to oppose the pressure, or to reduce the pressure, to shift to the left to reduce pressure, producing more reactants. There. 30 seconds left to go. I usually have a little bit more time at the end, and I don't like to rush at the end. But I was trying to explain to you as I was going through it. But yeah, this is all you have to know. I mean, this isn't all of the examples I'd like to know. I'd like to show you a better example where there's like a 5-mark question and you have to do the ICE table, because here they're kind of giving you some of the information, right? When I finish the whole of this unit again, then I'll probably do a big set of questions that hopefully have better examples. But that's it for this video.